Okay, when we start looking at the mathematical relationships for mirrors, recall that we have our focal length here. This is a concave mirror. We remember that because it's caved in, and your center of curvature here, and maybe we have an object back here somewhere. This is just our axis of symmetry, and there's our object. So our focal length is the distance from the mirror to the focal length. This is, we have a radius r here. So the first equation, we can say that the focal length will equal to that radius divided by 2. The distance here from our object to the mirror is going to be our DO. So DO is equal to object distance. And then whenever we form our image, we'll have a DI, which will be the image distance. We can also have a height of the object, so we'll use subscript O for that. So this is height of the object. So HO is equal to height of the object. And HI then would be image height. So we have a relationship here that's formed that 1 over the focal length is equal to 1 over the image distance plus 1 over the object distance. So there's one relationship we need to hold on to. We also need to hold on to that one. And then we just have some sign conventions that we need to go through. So the object distance is always positive. Focal length is positive for concave mirrors, and it is negative then for convex mirrors. DI is going to be positive for images on the object side of the mirror. And DI will be negative for the back side of the mirror. You can see then that the DI being positive, this will, if it's on the same side of the mirror, an image can be formed there, so this would also suggest that the image is real. And DI being negative behind the mirror, well, if you're behind the mirror, no real image can be formed, so this is a virtual image. And I think we talked about those terms before. Okay, so here your object is over here. Here's your DO, your object. So here is your object distance, DO. Let's say your image is formed back here, DI. Actually, it would be upright. So this would be your image distance here, DI. Here's your focal length. This would be your image height. And this would be your object height. Again, this would be a convex mirror. Okay, let's see if we can apply some of these. Oh, and one other equation we need in there in terms of is magnification. Our magnification equation is going to be equal to the height of the image over the height of the object, which is also equal to a negative DI over a negative object distance. Okay, so if we put all formulas up there again, so 1 over F is equal to 1 over DI plus 1 over DO, and the focal length is equal to R over 2. So those are really the 3 equations that we'll need to hold on to at this point. Let's take a look at an example. Okay, here we have a concave mirror, so we need to remember it's concave, has a radius of 30 centimeters, and an object is located 50 centimeters from the mirror. At what distance from the mirror is the image formed? Is the first question. What is the magnification and image height of the object if the object height is 25 centimeters, and describe the image in terms of the real or virtual size. So it's a concave mirror, so I always like doing a quick sketch just to make sure I have an idea of what's going on. So here's my focal length. It has a radius of 30 centimeters, and it has an object located 50 centimeters from the mirror. We want to know DI. So here is my object somewhere back here that is 50 centimeters from the mirror. So right off the bat we can find our focal length. Our focal length is going to be equal to r over 2, which is 30 centimeters divided by 2, which is 15 centimeters. So now we can go through and find our image distance. So using the equation that 1 over f is equal to 1 over the image distance plus 1 over the object distance, we can rearrange and solve for the DI. This is what I'm looking for. So 1 over 15, and the focal length is positive because it's a concave mirror, is equal to 1 over DI plus 1 over the object distance, and the object distance is always positive. All units are in centimeters, so we're okay there. So now we just need to solve for the DI. So 1 over 15 minus 1 over 50 is equal to 1 over the object distance, image distance. So 1 over DI is equal to 0.047. So DI then is equal to 21.47 centimeters. If we want to find then the magnification then is equal to a minus DI over DO, which is equal to a minus 21.47 divided by the object distance, again 50. So the magnification comes out to a minus 0.428. So right off the bat, this is less than 1, so it's a smaller image. It's negative, so the negative is going to say that we're inverted. So let's hold on to that. We also have this here. And then if we want to find the actual height, well, the magnification is equal to HI over HO. So the image height then is equal to the magnification times the object height, which is equal to 0.428 times the object height, which was 25. So the image height then comes out to 10.7 centimeters. So if we summarize this then, part A was asking for what is the distance the mirror images form. So DI is 21.47 centimeters. Part B was asking for what's the magnification and height. So M is equal to a minus 0.428. And the height of the image then is 10.7 centimeters. So C, we're describing the image. The image is inverted because it is a negative magnification. It's going to be smaller, 10.7 centimeters versus the original 25 centimeters. And lastly, is it real or virtual? It is a real image, and it is a real image because DI came out to be positive. We can double check that real quick if we take and draw our ray diagram just as confirmation. So here is our ray going that way. If we then take our ray through the focal point, it will reflect parallel, and the image is formed where those two reflected rays cross. So it is inverted, it's upside down. The arrowhead is below the axis of symmetry. It looks smaller, and it is upside down. And it's on the same side as the object, so therefore it is real.